Good morning, my dear students. Another Thursday, and we are with our online classes. I hope you have got the grade for your online examination and think of it and try to improve further. Today, we have to move with the topic of structure of fructose. So, the steps are almost same as that of structure of glucose. In this topic, we have to elucidate the structure of fructose in three different headings. First one is the open chain structure of fructose. Second one is the configuration of fructose. And finally, the cyclic structure of fructose. Moving to the structure of fructose or the open chain structure of fructose, we have to think about the experimental observations. So the first point is that from the qualitative and quantitative analysis, fructose is found to have a molecular formula of C6H12O6. Fructose on acetylation gives penta-acetyl derivative. Penta-acetyl derivative is only possible when the molecule have 5 OH groups. So this penta-acetylation clearly indicates that fructose molecule contains 5 OH group. Now see here, fructose on reduction with sodium amalgam gives a mixture of mannitol and sorbitol. We have seen this reaction. Fructose gives a mixture of sorbitol and mannitol. Now this clearly indicates that fructose contains 6 carbon atoms connected in a particular chain as in glucose. When fructose is reduced using hydrogen iodide in presence of phosphorus, it gives hexane. This clearly confirms the presence of 6 carbon atoms in the continuous chain form for fructose as in glucose, as same as in glucose. Fructose react with HCN to form cyanhydrin, and it react with hydroxylamine to form oxime. This clearly shows the presence of a carbonyl group in fructose. So this observation proves that fructose have a molecular formula of C6H12O6. Fructose contains 5 OH groups. Fructose is a straight chain compound and fructose contains a carbonyl group. Fructose on oxidation using concentrated nitric acid gives glycolic acid and tartaric acid. Both these acids have less number of carbon atom than in fructose. So tartaric acid contains 4 carbon atom, glycolic acid contains 2 carbon atom. And we know any ketone on oxidation with strong oxidizing agent will give you acids with less number of carbon atom than the parent ketone. So here fructose contains 6 carbon atom, but which on oxidation gives tartaric acid and glycolic acid both have less number of carbon atom than fructose. So this clearly confirms the presence of a ketonic group in the fructose molecule. Now we have to confirm the position of the ketonic group. We know aldehyde group could be only in the first position, while ketonic group could be placed any position between second and fifth. So we have to confirm the position of ketonic group. For that, we are taking fructose and we are treating with hydrogen cyanide. So hydrogen cyanide with react with the fructose gives cyanhydrin. We have seen this reaction. And this cyanhydrin is hydrolyzed followed by reduced with hydrogen iodide and phosphorus. So we have hydrogen cyanide treating with the fructose gives fructose cyanhydrin, which on hydrolysis followed by reduction with hydrogen iodide and phosphorus gives 2-methyl hexanoic acid. 2-methyl hexanoic acid. This clearly confirms the presence of ketonic group at the second position. So, since the ketonic group was on the second position, we are getting 2-methyl hexanoic acid. So, we could confirm that the presence of ketonic group is in the second position. Hence, the open chain structure of fructose could be represented as, see here, 5 OH group, 1, 2, 3, 4 and 5 OH group. And second position we have ketonic group, C double bond O, continuous carbon chain. So this is the open chain structure of fructose. Take down. Now we move to the second part of structural elucidation of fructose, that is configuration of fructose. You may be remembering the reaction of fructose with phenylhydrazine. Fructose react with phenylhydrazine to form fructose osazone, which is identical to that of glucose osazone. That means the osazone obtained from glucose and fructose are same. And we know when phenylhydrazine react with glucose or fructose, the reaction occurs in the first two carbon atom. All the remaining carbon atoms remain same. So we could say the configuration of third, fourth and fifth carbon atoms are same. While only we have to think about the configuration of first and second carbon atom in fructose. So the configuration of C3, C4, C5 and C6 are same for glucose and fructose. That is why the osazone obtained from glucose and fructose are identical or same. And we know osazone reaction occurs only to the first two carbon atom. So glucose and fructose only have a difference in configuration on the first and second carbon atom. In fructose, the first carbon atom is a CH2OH group, which is a non-symmetric or which is not an asymmetric carbon atom. Second is a C double bond O. Hence, the configuration of fructose could be established as CH2OH, C double bond O for the third carbon atom, OH on the left hand side, H on the right hand side, fourth carbon atom, OH on the right hand side, fifth carbon atom, OH on the right hand side, and finally CH2OH. So we could easily establish the configuration of fructose from glucose osazone. Take down. We have seen the open chain structure of fructose and we have established the configuration of fructose. But many of the observed phenomena or properties could not be explained using open chain structure. Hence, a cyclic structure was proposed for fructose molecule. And we know fructose exists in two isomeric form, alpha and beta. That means fructose exists as alpha D fructose and beta D fructose. So, open chain structure was not able to explain why there is alpha D fructose or beta D fructose. Open chain structure was not able to explain why fructose is having no reaction with sodium bisulfate, or we can say fructose does not react with the sodium bisulfate, which is a characteristic reaction of carbonyl compound. We know fructose contains a ketonic group, so it should give this sodium bisulfate reaction, but it does not give sodium bisulfate reaction. And fructose shows mutarotation. And open chain structure was not able to explain why fructose exhibit mutarotation. Hence, a cyclic structure was proposed for fructose by connecting the ketonic group present in the second carbon atom, that is the C double bond at the second position, with the sixth CH2OH group. So, a cyclic structure was proposed by connecting second ketonic carbon atom with sixth carbon atom by converting the second carbon atom to anomeric carbon atom. So, when a cyclic structure has formed, the second ketonic group becomes anomeric carbon atom. See here, this is the C double bond. This C double bond gets connected with the CH2OH group. So an oxygen linkage will appear, and that oxygen linkage, see here, this lone pair of electron is attacking here. So CO and H. So we will get a structure here. Now this carbon atom, second carbon atom becomes anomeric. Earlier it was not anomeric. Now it becomes anomeric or asymmetric. And if the OH is on the right hand side, it is alpha D fructose. If the OH is on the left hand side, it is beta D fructose. So this is the cyclic structure of fructose. Take down, very important. You please draw alpha also. I have drawn only beta. You have to draw alpha also. Howarth compared this structure with pyrene molecule, and he proposed a fructopyranose structure. We have seen the same case in glucose but bit different here. So by comparing to pyrene molecule, which is a six-membered heterocyclic molecule, Harvard proposed a structure. See here, this is the first carbon atom, this is the second carbon atom. If the OH group is on the left hand side, it is beta D fructose, and if this OH group is on the right hand side, it is alpha D fructose. So the connection is between the second carbon atom and the sixth carbon atom. Now sixth carbon atom is having a CH2 group while the second carbon atom is having a CH2OH group. So Harvard connected with Piran and he proposed a Pirano structure. See here, this is the oxygen atom which is connecting the second carbon atom. This is the first carbon atom, second carbon atom, third carbon atom, fourth, fifth and sixth carbon atom. So the second carbon atom is the anomeric carbon atom. So this is the anomeric carbon atom. If the OH group is on the left hand side, it is beta D fructose. If the OH group is on the right hand side, it is alpha D fructose. And any structure on the right hand side will be below the plane. We have studied in glucose molecule. Same thing here. So here the OH group is on the right hand side, means alpha D glucose should be on the below the plane. Hence it is alpha D fructose. Take down. Now see here, H on the right hand side, below the plane. OH on the right hand side, below the plane. OH on the right hand side, below the plane. Moving to here, CH2, one H above the plane and one H below the plane. So this is the Pirano structure or alpha D fructopyranose. When it becomes beta D fructose, this OH group will be at the top position and CH2 group will come to the down position. So only the configuration changes at this carbon atom, that is the second carbon atom, that is the anomeric carbon atom. So in alpha D fructose, the OH group is below the plane, and in beta D fructose, the OH group, this OH group will be above the plane and CH2 group will be below the plane. Okay. So we have seen the cyclic structure of fructose and the fructopyranose structure, which is a six-membered ring. But it has observed that in many polysaccharides, fructose exists as a five-membered ring rather than a six-membered ring. So, in many polysaccharides, it has observed that five-membered ring structure is there for fructose rather than a six-membered ring structure. That means six-membered ring structure is immaterial for fructose and five-membered structure is important for fructose. So, a five-membered structure was proposed by connecting with a compound called furan. This is furan molecule. This is furan molecule. In this furan molecule, we have first carbon atom, second carbon atom, third carbon atom, fourth carbon atom. So, four carbon atoms are connected with an oxygen. So, in furano structure, we have to have a connection of oxygen with second ketonic carbon atom and fifth carbon atom. So we are again restructuring fructose molecule by connecting the second ketonic group, that is C double bond O group, in the second position with the fifth carbon atom. We know fifth carbon atom is having a CHOH group. So that structure is proposed. See here, this is the second carbon atom. This is the first carbon atom. This is the second carbon atom. This second carbon atom is connected to fifth carbon atom. Sixth carbon atom is remaining here. So we are not touching the sixth carbon atom. We are connecting to the fifth carbon atom through an oxygen linkage. Now the second carbon atom become anomeric. So OH group could be on the right hand side. It is alpha D fructofuranose. If the OH group is on the left hand side, it is called beta D fructofuranose. So, by connecting the second carbon atom with the fifth carbon atom, a cyclic structure was proposed. So, second carbon atom with fifth carbon atom. OH group on the left hand side, beta D fructose. OH group on the right hand side, alpha D fructose. But this is a connection with the furan molecule, so it is fructofuranose. Take down. See here. This is alpha D fructofuranose. See here. All the groups attached on down. See, this is the oxygen connection. See, first carbon atom, second carbon atom, third, fourth, fifth. So fifth carbon atom and second carbon atom oxygen connection. See here, first carbon atom, second carbon atom, third, fourth, fifth. So fifth and second carbon atoms are connected. Here also first, second, third, fourth. So first, second, third, fourth, fifth, sixth. So second carbon atom, fourth, third, fourth, fifth carbon atom connected. So here OH group is on the right hand side, below the plane. H group, right hand side, below the plane. OH group, right hand side, below the plane. Here H down, since CH2OH group is a bulky group, it is above the plane. Now see here, this is beta D fructose. All the configuration are same except for second carbon atom. For second carbon atom, for beta, the OH group is on the above the plane, while CH2OH group is below the plane. So all the configurations are remaining same except the configuration of anomeric carbon atom, that is 2. So this is the structure of alpha D fructofuranose and beta D fructofuranose. Take down. So take down this also.